Welcome to CO 738 Probabilistic Methods. Today we'll be discussing Dependent Random Choice. So what is Dependent Random Choice? Well, at a high level, the idea is that making the desired outcome deterministically dependent on an associated random choice. So if we're trying to solve a problem with the probabilistic method, we're tempted often to just make a random choice and have that be the desired outcome. But here, the idea is more subtle, that we use a random choice and then from that, extract an outcome which deterministically depends on that random choice. So this is a bit not what we're used to with the random method, with probabilistic methods, just making a random choice from the get-go. More specifically, the dependent random choice is a probabilistic method that shows how to find a large set of vertices in a dense graph, such that every small subset of vertices has many common neighbors. So this high-level idea has mostly been applied to this one more specific problem, where we want in a dense graph to find a large set of vertices where every small subset has many common neighbors. And what's the idea to that? How does that tie in with the high-level idea I said above? Is what we're really going to do here is randomly choose a subset of vertices. Now that random choice may not have this property very well, but then we're going to deterministically choose their common neighbors. So how do we find a set where many of the small sets have many common neighbors? We kind of choose the neighbors randomly. So we choose a random set and then we backtrack and deterministically say, okay, what vertices have these as common neighbors? And that might not work out. We're going to use alteration to make sure that every subset has that property. But that's the rough idea. And intuitively, this should increase the chance that small subsets have many common neighbors instead of just picking some random set and hoping this. So that needs to be borne out in practice, of course, and we'll get to the details and the conditions to make this work. But the hope is by somehow randomly choosing a set and then deterministically choosing their common neighbors, we can hope that it's very likely that most of these sets actually have many common neighbors. So that's the high-level idea. Now let's see it in practice. So there's what I'll call the dependent random choice lemma. So there's one main lemma that does this, and it goes as follows. So we let a, b, and an r be positive integers. Don't worry about what those are yet. And then let g be a graph on n vertices. So n is the number of vertices with average degree d. So I didn't say d above. D will come in a second, but d would be the average degree, which of course is defined as twice the number of edges divided by n, by handshaking. And now here's the assumption. We're going to assume that d is somewhat large. So we get this somewhat monstrous equation. So if d to the r over n to the r minus 1 minus n choose r times b minus 1 over n to the r is strictly greater than a minus 1. So somehow this is saying if d is large in terms of n and r and a and b, then we get a nice outcome. We get that there exists a subset a0 of v of g with a0 at least the size of a, such that every r vertices of a0, so every r tuple there, have at least b common neighbors. So now that you've seen it in full, you can see what the parameters do. So n is the number of vertices, r is the size of the tuple we're interested in, so we're looking at r tuples. We want to find a set a0 with a0 least size little a, so a is telling you how large a set we want, and then b is the number of common neighbors we desire. So we want a set of at least a vertices where every r of them have at least b common neighbors. And the claim is that if we have a graph on n vertices and that average degree is large enough, so if we have a dense enough graph in terms of these parameters to satisfy that equation, we will get that. Now you might not know what good this is, but we'll come to applications at the end of the lecture. Let's proceed on. I will say some history that early variants of the lemma were proved by Kostachka and Rodel in 2004 and by Gowers in 1998. And we follow instead the proof of Alon, Karvelovich, and Sudakov from 2003. So how is this going to work? On to the proof. So we're going to let T be a multiset of R random vertices of G chosen uniformly with repetitions, right? So instead of just randomly choosing our A0, we're going to apply this idea of randomly choosing a set and then choosing their common neighbors. And the strange thing here is we're going to allow repetitions. So that's, in some sense, to smooth the analysis. It doesn't make maybe too much difference, but it's quite a nice idea. So we're going to choose our random vertices, but with repetitions, right? So each vertex could be chosen more than once. And now what do? We're going to define A to be the vertices in V of G, where T is a subset of N of V. Or equivalently, so A is somehow all the vertices who have T as, are in the common neighborhood of T. All right, so then where do we go from here? We're going to let X be the size of A. And what are we interested in? We're going to be interested in the expectation of X. So to get to that, what's the chance a vertex is in A? Well, the probability that V is in A, what is it? So I claim it's d of V over n to the r. Why? Well, I'm choosing these vertices at random, so each vertex has a 1 over n chance, it's uniformly. And I have d of V neighbors, that's the degree. So what's the chance? I need each of the choices to be a neighbor, so I have each choice being d of V over n to the r, as they're independent. And here it's key, we're using with repetitions, so I don't have to do somehow following factorials. Really, each time I can have a d of V chances to get a neighbor there. So that's the probability that an individual vertex is in A. It goes with the degree. It's degree over n to the r. So by linearity of expectation, the expected size of X is the sum, of course, over all the vertices of the probability, which, as we said above, is degree over n to the r. And this is, you can write as 1 over n to the r times the sum of these degree to the r. Right? We can just take out that 1 over n to the r. It's just a constant factor. Now, where do we go from there? You might notice the sum. Now, remember, r is an integer. It's at least 1. So in particular, by the convexity of the function x to the r, you might recall then by convexity that this sum actually has to at least be somehow the sum of the averages. So what does that mean? That the sum of the d of v to the r has to be at least n, because there are n terms there, times the average degree, which we've called d, to the r. So that's by convexity. And now we can plug that in and find that the expectation of x is at least n times d to the r for that sum above, divided by n to the r, which is d to the r over n to the r minus 1. And that should seem familiar, as that is actually the first term from that crazy equation. So that's the beginning part. But now we have to worry about maybe the set X, the set A doesn't actually have that property that all the subsets have many common neighbors. So we're going to proceed, just for notational purposes now, for a subset S of V of G, I'm going to let n of S be those common neighbors, so the intersection of V and S of n of V. And now we can proceed to discuss those R tuples with few common neighbors. So we say S in V of G choose R, so an R tuple is bad if n of S, that's the common neighbors, the size thereof is smaller than B. So these are the ones we want to avoid. And so we'll let Y be the S subset of A, so those R tuples where S is bad, that are in A. And we would like to avoid all of these, so let's calculate the expectation of Y. To do that, for a big R in V of G choose R, what's the probability that R is a subset of A? So that this bad tuple ends up in A. Well, what do I need? To be in A, I need that all of the vertices in T are neighbored to a vertex in R, and I need that for all the vertices. So that means every time, every vertex in T needs to be a common neighbor of all of R. And so that means that we have to choose one of the common neighbors of R for each vertex in T. There are n of R size thereof choices, and so the probability at each choice is that size divided by n, and to the r since we're with repetitions. So that's the probability that a given bad tuple is, or just a general tuple is an A. Now for bad tuples, the n of R would be at most b minus 1. And so hence we can take the expectation of Y by linearity of expectation is the sum over the R's are bad, the probability that R is a subset of A, which as I said then is at most the sum when R is bad of b minus 1 over n to the R. Since the number of common neighbors, since they're bad, is at most b minus 1. So that'd be an upper bound there. And now what do we do with this sum? Well, I'm just going to be a bit naive here and upper bound this with all the possible sets. So we'll just say this is at most n choose R of b minus 1 over n to the R. So we'll hope that n choose R isn't too bad. And now where do we go from there? Well, by linearity of expectation, what's the difference between x, our size of our set, and these number of bad r tuples in our set? So what's the expectation of x minus y? It's, of course, the difference of those two, which then is greater than or equal to d to the r over n to the r minus 1. That was the lower bound for the expectation of x. And we had an upper bound for the expectation of y of n choose r b minus 1 over n to the r. And that might seem familiar because that second term is now the second term from our equation, and so we can use that inequality to say that this is greater than a minus 1, where the last inequality follows by that assumption. So now we're almost done. We know that the expectation of x minus y is greater than a minus 1, and so it's at least a. And so what are we going to do? We're going to use our alteration. So here we use another probabilistic method we've covered, alteration. So we're going to alter our set x with these y. How do we do that? Well, so by expectation here, there exists a t such that x minus y is at least a, because those are integral. And so what do we get? Well, so we know that there is this choice where x minus y is at least a. So for every si in that a that we get, where si is bad, we choose a vertex vi in si. So somehow we just want to get rid of these bad tuples. We're just going to delete a vertex from each of them. So that's precisely what we do. We let our final a naught be a minus those chosen vertices. And that means that the size of a, well, a naught, well, a started out at size of x there, and we subtracted, worst case, a different one for each one. So worst case, this is at least x minus y, which by assumption was at least a. And every r tuple of a naught has at least b common neighbors because we avoided all of the bad tuples as desired. So that's quite a nice proof. We used alteration. We used this dependency from the random choice to get that. And we calculated the expectations. And of course, we used that inequality as an assumption. So let's talk about applications of dependent random choice. We're just going to do one main one here, which is about Turan numbers. So you might recall that the Turan number of a graph H, denoted Ex of NH, is the maximum number of edges in a graph on n vertices that does not contain H as a subgraph. So in extremal graph theory, we're interested in this idea, how many edges, this question, how many edges can you have if you don't contain a given graph H as a subgraph? And some of those are quite well known and understood. In particular, there's Turan's theorem from 1941 that says the extremal number, the Turan number of nkr is at most 1 minus 1 over r minus 1, n choose 2. So somehow the best you can do is somehow an r minus 1 complete partite complete graph there. And actually those are called the Turan graphs, and Turan actually further showed that those are the only extremal examples, the only ones that get an equality there. We won't prove this. I proved it before in one of my other classes, so you can check that out in the description below. But this gives us an upper bound, so we're not going to care about the extremal, but just we know the Turan numbers of the complete graphs. And then the big question, though, is for every graph H, what is the Turan number of H? So what about for other graphs, not complete graphs? Well, let Ks star R denote the complete R-partite graph with S vertices in every part. So there's a famous theorem of Erdős and Stone, which I've also covered in my graph theory class. Again, link in the description below, where for every integers R at least 2 and S at least 1, and for every gamma greater than 0, there exists an N0 such that every graph with at least that many vertices and at least the Turan number of Kr plus gamma times n squared edges contains KSR as a subgraph. So what is that saying? That's saying if you just have a little bit more than the Turan number of Kr quadratically, so if you just have a quadratic, a little bit more edges, then what do you get? Not only can you get a Kr, but really you can get kind of a blow up of Kr. So we can get this R-partite graph where there's S vertices in each part. So we can blow up each vertex and then complete graph to size S. And what does that give us? Well, then an easy corollary of that, noticed by Erdős and Simonovic in 1996, is that for every graph H with at least one edge, that the Turan number there is 1 minus 1 over chi of H minus 1 plus little of 1, n choose 2. So that's quite nice that you can actually basically determine somehow the Turan number is intrinsically linked to the chromatic number, right? Because it's saying all these R-Bipartite graphs, these blowups would be that amount colorable. And so if you're that amount of colorable, if we can put you into this R partition, then indeed we can get it with roughly 1 minus 1 over R minus 1, which is 1 minus 1 over the chromatic number minus 1, with some little order term there. So that essentially tells us what? Well, if we have chromatic number at least 3, this gives us the Turan numbers, up to those little order terms. The issue is that what happens when chi is 2. So the previous theorem implies that H is bipartite, that front constant just goes away, and so the Turan number of H is little o of n squared. So it's subquadratic. Unfortunately, that doesn't tell us what the Turan number of H is. So for all other graphs, we have a very good idea exactly it's quadratic and there's some constant. For the bipartite graphs, we just know they're subquadratic. And so a big question is, what is the order of these Turan numbers when H is bipartite? And that's still open for lots of graphs, and we don't have a good handle really on what they could be, but we have some results. And so in particular, there's the following theorem. Let H be a bipartite graph with maximum degree R on one side. So I'm thinking kind of bound to max degree, but just say it's bounded on one side. Then I can tell you there exists a constant C depending on H, which is greater than 0, of course, such that the Turan number of H is strictly smaller than C times n to the 2 minus 1 over R. So if you somehow can tell me that I'm bounded degree on a side, then actually I can improve that subquadratic bound to something even polynomially smaller with this minus 1 over R in the exponent. Now that might not be tight, but that's still improvement. And in general, though, it's sort of tight in that it's tight for all values of R as follows. It is known that for every R and for every t greater than R minus 1 factorial, there exists a graph G with n vertices with at least CRT, that's some constant depending on R and t, times n to the 2 minus 1 over R edges, and no copy of KRT. So there are indeed, if we're looking at just KRT, that complete graph there, that complete bipartite graph, where t is rather large, then actually we can find graphs with many edges that don't contain KRT as a subgraph. So that tells you that the Turan number of these rather unbalanced complete bipartite graphs meets this bound. So if you view then kind of R as fixed and H as free, then it is tight. But if you're somehow not complete or not too unbalanced, maybe we could do better, and that's still open in a lot of cases. So let's just prove this theorem. How are we going to prove it? We're going to use our dependent random choice lemma, of course. So here's how the proof goes. We'll let H equal AB, that's a bipartite graph, and we'll assume without loss of generality that for every vertex in B, the degree of V is at most R. So we had one side with small degrees, so we'll assume that side is B. And then we're going to let little a be the size of A, that one side, and B be the number of vertices of H. And then we're going to let C, so we have to somehow find a constant there, we're going to let C be a constant that satisfies C to the R is strictly greater than B minus 1 to the R over R factorial plus A minus 1. So why are we doing that? It's to make the dependent random choice lemma work, and you'll see how that goes. And now what are we interested in? We're going to let G be a graph with n vertices in average degree D, and we're going to assume that the average degree D there is at least this C above times n to the 1 minus 1 over R, right? So we wanted to make some C that works, so we wanted somehow the number of edges being more like n to the 2 minus 1 over R, and so if each vertex had at least this degree, if that's kind of the average degree, then indeed the number of edges would be as in the theorem. So what do we go from there? It suffices to show that G contains a copy of H, right? So if we can show that every dense enough graph contains a copy of H, then surely then the Turan number must be smaller than this bound. So how do we find copies of H? Well, we're going to use the dependent random choice lemma, so let's try to verify that holds. So we have our average degree D. I just have some lower bound there. So we want to check that D to the R over n to the R minus 1 minus n choose R times B minus 1 over n to the R was at least A minus 1, if you remember. And what do we have? Well, if I just plug in that lower bound on D, then what do we get? We get a C to the R, and it turns out that those n to the R minus 1 and n1 to the 1 minus 1 over R to the R, those cancel. So that first term will just be at least c to the r. And as for the second term, I can just replace n choose r with n to the r over r factorial, since we're lower bounding here. And we get b minus 1 to the r over n to the r. Those n to the r's cancel. And so we get c to the r minus b to the minus 1 to the r over r factorial, which by assumption was strictly greater than a minus 1, because that's what we picked c to satisfy. So basically we pick c, it works out there's just kind of a constant depending on a, b, and r that will indeed get us that this dependent random choice lemma holds when we plug in that kind of average degree. So we're almost done. By the dependent random choice lemma then, now it holds, there exists an A0 subset of V of G, with A0 being of size A. Technically I stated it as being greater than or equal to A, but you could just pick a subset of that size, such that every R vertices of A0 have at least B common neighbors, right? So there was a large subset where every R vertices had many common neighbors, so here B. And now we embed H and G as follows, right? So we have to find this copy of H, and I'm going to say, well, now that we know about the set A0, we can actually embed the graph H. So we can actually find the copy. So we're kind of embedding, meaning we'll do it a little bit at a time until we're satisfied that we found indeed a copy of H. So how does this go? Well, let phi be a bijection from A to A0. So I don't really care how you do that. So really just label all of A, that one side with names, label A0, take an arbitrary bijection. So we just embed them. It's an independent set, so there's nothing really to do yet. Now we have to embed the B side. So how do we do that? Well, for every BI in B, so in our original graph H there, we let SI be the image of NH of BI. So what does that mean? So we had these neighbors of little BI on the A side. All of them got embedded, mapped somewhere into A0, and let's consider that set. So that set, well, I claim we can choose a phi of BI, so an image for BI, that's the embedding, that's in the common neighborhood of all of these, of all this SI, all the vertices in SI. And I'm going to make sure, though, that I don't use any previously embedded vertices images. So delete phi of bj, where j is smaller than I. So again, more informally, what we're doing is we successively embed the vertices of B, so they have the desired neighbors in A. So right, A got mapped. We successively embed B to make sure it has the appropriate neighbors on the A side. And the only trick, though, is we have to avoid the previously chosen vertices of B, right? We want to make sure they get different images. And so we can do that if the set above is actually large enough, right? So we need that there are lots of common neighbors to avoid the previously chosen. And indeed, this is always possible since ng of SI, by assumption, is at least B, right? So every SI there had at least B common neighbors. And so what does that mean? Since there are B vertices, little b vertices in big B, then I can always avoid the at most B minus 1 previously chosen ones to find another common neighbor that will work. And then that concludes the proof. So we can use our dependent random choice lemma to successively embed these sort of unbalanced bipartite graphs with small degree at least on one side, and that ends up working then to give an upper bound on the Turan numbers of such bipartite graphs, which are quite hard in general to determine, but we can get a nice upper bound. So that's really all for today. We studied the dependent random choice lemma, which is a really nice idea, nice proof technique of making a random choice and then making some further choice deterministically dependent on that. In particular, to show that there is a large set in every dense graph where every small subset has many common neighbors, and we apply that to the Turan numbers of bipartite graphs. So until next time, see you then!